So last time we were talking about this equation, we were talking about the variational principle, and we arrived at this point. And do people remember what was the purpose of the variational principle? Like, what were we trying to get to?
Like the assumption or the known result that will always be greater than the true energy.
Yep, that was true. What were you going to say, Maddie?
To minimize the E.
Yeah, we're looking to have the lowest energy we possibly can, and we're looking for the wave functions. These C's are the contributions of the basis functions to the system. What was like HAA, and like what's SAB? Actually, this
That's the overlap.
Yep, these are overlap integrals. And then what are, like, what's AB, HBB, that stuff?
Isn't that just the, like, your integral, but with the, like, an operator in it?
Yep, and that's the Hamiltonian, right,
Mhm.
operator that's in between each of these. Yep. Okay, so now how do we find this lowest energy? Well, we said previously we want to look at derivatives and we want to get the expression set to 0. So that's what we're going to do. Before we do that, we're going to make things a little bit easier. Instead of having to write this big long thing out constantly, what we're going to do is, let's get this thing to focus. We're just going to shorten the top to N and the bottom to D. So top for numerator, D for denominator. Okay, so if we take the derivative of this guy with respect to some constant, one of these two constants, of energy with respect to K sub C, C, E, we get this expression.
Is this a partial derivative?
Yes, this is partial derivative. It could be just written as a regular derivative, but I like it as partial. Okay. Let's try to simplify this. How would you simplify this expression?
Cancel. Oh, no.
Mm-hmm.
Oh, cancel out one of the D's. No, you can't do that.
Yeah, apply one of the D's through, and what's going to happen is this is going to cancel out.
Good job, doctor.
Yeah, it's whatever.
That makes this a little bit easier to solve. Okay. And then this expression, we've seen it somewhere before.
That's the E thing.
Yep. There we go.
What is that called? Epsilon?
Yep, that's epsilon.
Okay. Curly
E. I know we don't have Dorito or a shark fin or anything for this one. So.
Backwards 3.
There's some loud ass birds out of somebody's house right now, or what is that noise?
I have my window open. Do you hear them now?
Yeah. It's actually pretty calming. I like it.
Yeah.
Everybody else nuts. So now what we're going to do, we're going to set this derivative equal to 0, and we're going to get a solution that way. Okay. So like that. Okay, what would you do to make this a bit simpler?
Multiply d to the other side.
Yeah, multiply d, and then that would be 0 here, so we wouldn't have to worry about it. So we could just move that over. So we got, what is it? NC minus E T of D is equal to 0, which is also equal to that, oops, epsilon divided by derivative with respect to KC. Okay.
Why doesn't this epsilon need to be in the little brackets?
Like this guy, oh, like that,
Mm-hmm.
as an expectation value.
Okay.
Yep, that's an expectation value, so we don't really have to worry about it in this case. All right, so now we have two constants. What are those two constants with our system that we're concerned about?
Would it be D and N?
Well, we have d and n. That's like the numerator and the denominator of this big long expression. That's just a shorthand for this guy. But what constants do we have to solve for to know the energy of the system?
CA and CB.
Yep, we have to know CA and CB. So we have CA and CB to differentiate by. So N, we said, was this expression, just that top part. CB squared, HBB, 2CA, CB, HAB, and D was equal to CA squared plus CB squared plus 2CA, CB, SAB, like that, right? Okay. So now what we're going to do, we're going to take the differential with respect to CA of N. So this guy up top. If we take the derivative of the top with respect to CA, what are we going to get?
Would it be 2CA? HAA?
Yep. Plus, what happens to this term?
That'd be the same because there's no CA.
Yeah, so, yeah, or so we take a derivative of something and we don't have.
All constants. So
Yep.
it's just 1
Not 1.
or 0.
0, yeah. And then this portion, what's that? What's going to become with that?
Must be 2 CB HAB.
Yep. And if we do the derivative of D with respect to CA, so this guy, what are we going to get out? First term?
2CA oh wait, yeah, just 2CA.
This guy?
0.
0.
Last term?
2CB SAB.
Yep.
This is with respect to CA.
Yes.
Okay.
So we get the following, right? Two CA plus 2CB SAB. Okay, so now what we're going to do, we're going to plug these expressions back into this guy. Let's
On that bottom one, doesn't
Mhm.
that see wait, Sorry, what happened in your second step? Of like the derivative of d with respect to CA? Okay,
Yep.
never mind. I was just reading the symbols wrong. Never mind.
Okay. It's okay. Imagine that, not being able to read my handwriting. Surprise. Okay, so now what we're going to do is we're going to take these things and we're going to plug them back into this expression. Epsilon d, like that. Okay, so let's take those and plug that stuff in. So we get 0, which is also equal to ECA. So we need the derivative with respect to n, or n with respect to CA first. So we get 2 CA, HAA, CB, HBB minus E times, what are we going to multiply E by?
The second term of 2CA, 2CA SAB.
SAB, right?
Yep.
Okay. Now, let's multiply everything through. CB, HBB minus epsilon.
Isn't that the H, not BB?
I'm sorry, what was that, Josh?
For the second term, it should be 2CBHAB.
Yeah, you're right. I'm sorry. Good catch. There we go. Plus, oops, nope. Still should be a minus epsilon 2CB SAB. Okay. What we're going to do now is we're going to group all the CA terms and all the CB terms together. Is there any other way you could make this a little bit easier, knowing that this is equal to 0?
You
Mm-hmm.
just move, I guess, whatever side you'd like to the other side. So, I mean, I'd probably move the negative terms over.
You could do that, but we're going to leave them this way because it's simpler to solve that way.
Okay.
So you want to group the CA terms together? Is that what you're
We
saying?
want to group the CA terms together, but can we get rid of anything else before we do that?
I can
Yes,
divide by
two.
something.
Can we divide by what?
You can get rid of the 2.
Yep. All these 2's can go away. Whoops. Taking my camera with me. Yep, all of those can go away. So now let's group the CA terms together. Get CA times, what are we going to have in our brackets?
It'd be like 1 minus epsilon.
Yep, so we get HHA minus epsilon.
All right.
Yep. Plus, let's get all the CB terms together.
That's a parenthesis, not a CHIA.
Yes, that is a parenthesis.
HAB
Mm-hmm.
minus epsilon SAB.
Yep. Okay, and that's all equal to 0. And you could show the same thing is true. We could show we could do the same thing for CB and show that the differential with respect to CB is equal to CB H BB minus epsilon plus CA HAB minus epsilon SAB is equal to 0. And now these expressions along here, these equations along here, these are called the secular equations. And you guys saw a little bit of those in your Quizlet. And you can solve these equations simultaneously. And that's where you end up with what's called the secular determinant. Simultaneously. You end up at what are known as the secular determinant. So in our case, let's see. Yeah, we'll leave it that way for now. So with our two basis functions, it would be HAA minus epsilon SAA minus HBA minus epsilon SBA HB epsilon SAB HBB minus epsilon SBB. And that's all equal to 0. So that's another way of looking at it. Let's just jump back to the secular equations because it's going to be a bit easier for us to look at. Okay, or to more simply state, the secular equations sorry, I should have been in parentheses. I don't know why I got excited. I put an exclamation point. Alpha A minus epsilon CA plus beta minus SABE CB is equal to 0 minus epsilon CB plus beta minus SAB epsilon CA is equal to 0. Okay, what are these alphas? What are these betas? And this is kind of the not nomenclature, what is it? This is the way your book expresses these. Notation, there we go, that's the word I was searching for. So where alpha I is equal to HII. And what did we say HII was again?
Probably equal to 1 or 0, 1.
Nope, not a 1 or a 0.
Okay.
You told me at the beginning it was like the integral.
Oh, yeah, so it's just the integral of your one function, yeah. And then you have your Hamiltonian
Yep.
by the regular function.
Yeah, exactly. And what this is commonly referred to as, this is known as the Coulomb integral. And it's usually negative.
Should the other psi be psi I, or is it just?
Oh yeah, yep. It should be a psi I. So this Coulomb integral is usually negative. What does that mean? Is it energy raising or energy lowering?
Lowering.
Raising.
Lowering. Negative usually means lower in energy.
I
Yeah.
knew that, but I thought it was the opposite for this.
Like
I know, it's one of
exothermic
those
versus
things.
endothermic signs.
Is that like the repulsion is positive then?
Repulsion
I
is
thought one of them was-
positive. Yep,
Yeah.
repulsions are positive. And basically what this is keeping track of is it's the energy of the electron when it's contained within orbital I. So energy of electron in orbital I. Okay, what about beta? Beta ij is equal to hij. What's that equal to? Like, what does that mean? What were we gonna say, Tara?
Can you move it over a little?
Like this way or this way?
Nope, other way.
That way?
Yeah.
There we go. So what does hij mean?
Just means that your two functions are different.
Yep.
It was like, is that really just saying that when you take the conjugate of it, that it changes? So it has an I in it?
Yeah, with the complex conjugate, yes. So if you have a complex conjugate, whatever was positive I becomes negative I.
Yeah. So that's like all that's really meaning, because like, how else could it change?
That's about it.
Okay. About it.
And that's as far as I know. There's probably some weird mathematics.
Oh,
thing
yeah.
that's way more in depth. Now this beta integral, this is called the resonance integral. And what it's looking at is it's the strength of the bonding interaction between orbital I and orbital J. So what it does is it keeps track of the strength of interaction. As a result of overlap of orbitals I and J. Okay. If there is constructive overlap, is that energy lowering or energy raising?
Lowering.
Raising.
Energy lowering. Now,
I'm done.
now, if
Pretty
it's if it's energy lowering, is it going to be negative or
That's
positive?
negative.
Yep, it's
Hey.
negative. There we go.
Atta girl.
Killed too many brain cells after I heard I passed my SEM.
That's after I passed both of my. So I had to do a seminar in undergrad, and then I had to do my like a couple of them in grad school. But the one I got done with in my undergrad, like my mom and dad came and my girlfriend against my wishes. And I was like, I wanted to go to bed and all they wanted to do was celebrate. Same thing happened after PhD defense. And then I drank snake wine.
Snake wine.
Look it up sometime. What they drink in the Philippines to show it in them.
I think I know what you're talking about. Yeah, it's
I've seen it. I've never
Worst drink
Where
I've
do you
ever had
get
in my
that
entire
around?
life.
Oh my god.
It's got a
Where
cobra
would
in
you-
it.
Interesting.
yeah.
That's a
Where would you
cobra,
buy
yeah.
something like that around here? You have to
You
make it.
can't. I don't think
You
you're
can't?
invented.
So where'd you get it?
Probably illegal in the States.
I can't disclose that information.
he made it himself. It's
Probably
prison.
black market.
Made
But
himself.
Actually, well, I mean, hey, there was that guy along in Allegheny who is like,
Oh,
who had
yeah.
all those cobras and stuff. I don't know.
There is more reports of illegal lizards being kept in Olean and Allegheny than I've ever heard of anywhere. Every year there's something.
I
Pretty
don't know
crazy.
why.
I don't either. I don't get it.
It's kind of awesome.
That and meth labs in the microtel.
Yeah, that's a big time. We're not Allegheny County though. They have way more.
YouTube video is sponsored by
I'm
microtel.
just kidding.
Stay
Get
one
there.
night for $40.
Oh, get
This
roasted.
is also the stabilization energy. It's keeping track of, like when you think of constructive and destructive overlap, this is what we're discussing. Okay. So like I previously said, we can throw these in a secular determinant. They can both be solved simultaneously. So these equations, oh, I should have said secular equations can be solved simultaneously.
So that's all that secular means?
I think it's just a fancy name. So with the secular determinant, we're looking at trying to minimize the energy. We have alpha minus epsilon, beta AB minus SAB epsilon, beta minus SAB epsilon, alpha B minus epsilon. And we're going to come back to that a couple times, especially when we get to Huckel theory. Hopefully we can do that relatively soon. That might just be the next class. Okay.
Always next semester.
Yeah. Not for
yeah,
everybody.
hopefully, yeah, next semester. It's a great
guys.
timing.
Yeah, we'll do it all next semester.
Yeah.
Aw.
When it's only the serious chem majors left.
Yikes.
Those committed to
Yeah.
Bonaventure.
I'm willing
That's
to grind
Yeah.
it out at Bonaventure. Can you guys say the same?
it. All right, let's solve this. What do we got to do?
Oh, is this a determinant? Yeah, okay. So
Determinant. So tell me some math. What are we going to multiply together?
left
Fish
times
times
bottom
fish
right
minus B times B.
minus.
Yeah, those guys together. Fish, Jesus fish, minus epsilon.
Yeah.
Catholic
Beta.
How religious Dr. Simpson is.
Take our Franciscan teachings here.
Oh, yeah,
to heart.
seriously.
He has a portrait of Jesus.
Yeah,
He knows.
yeah, I
Oh
gotta-
yeah. wait a
I
second.
gotta
Look at the
maintain it to the
background.
high man right there. He's
Yeah.
watching me.
Is it a hologram?
No, it's like a
Said it's
blue
a
painting.
hologram? What?
Well, it is I don't know. For the colors of it, I would expect it to be like 3D or something.
It looks 3D. It used to just creep me out as a kid, really, really bad.
So you hung it up in your office.
Yeah.
What else would you do?
Make sure he's watching over you. Yeah.
Soon it'll be in the nursery.
I was just thinking that.
Oh, I couldn't explain it. My poor
How to
daughter.
scar your child for life.
Well,
Poor daughter.
hey, but it made at my grandma's house we weren't allowed on the furniture, so we always just said like like he would judge us if we ever sat on it. We never tried to.
Gosh.
Oh my god.
Minus beta S8 B epsilon. Oops, I forgot. We forgot some symbols in here, didn't we? AB. I guess I didn't have to write this out twice, but that's okay. Okay, we can run to kind of the punchline with this. What you get in the very end is epsilon squared minus 1 minus SAB squared plus epsilon 2 BABSAB minus alpha A minus alpha B plus alpha A, alpha B, beta AB squared. All that's equal to 0. Okay. We can actually solve this. How are we going to solve this?
It's a polynomial, so
Yeah, polynomial. So what are we going to do?
quadratic, I'm assuming.
Yeah.
Slap that
That's
in the
terrible.
formula.
Quadratic equation.
Oh God.
All right. Anybody remember quadratic equation? What is it?
Yeah.
That.
Negative b plus or minus square root of b squared minus 4ac over 2a.
Oh
Wow,
man.
buddy. We're impressed.
Yeah, it's the one thing I know on my Diffie-Q test.
I don't think you do that in DiffyQ.
I was gonna say I
You do.
don't think that's DiffyQ anymore.
I don't remember doing that.
You do if you can't factor your a for your straight line solution.
Ah,
Ooh.
okay.
That is
So
the one
what's-
thing I knew on the test besides my name.
Sounds like my Diffie-Q class. It was awful. A. What's going to be our A?
1 minus SAB squared.
Mm-hmm. Beta? Or excuse me, B?
2 Bab Sab minus fish A.
Ab and Sab.
Couve and Duve.
Oh, never forget.
Thought we forgot about that one.
I haven't brought it up in a while.
Yeah, it's been a minute.
Well, you should be bringing it up. You guys got an inorganic final to study for.
Oh.
That was so funny.
That was.
Wait, can we just make that a take-home one too?
Say it louder, John.
Yeah, I think we should just make that a take-home one.
Nah, one of them gets to be take home.
One of them. Just
Get
one
to
of them.
pick. All right, so we got that.
I'd probably choose inorganic.
All right. So what we end up with is a really long, complicated expression, which we're going to write out very shortly. I meant in time, not in length. We got alpha A plus beta, or alpha B minus 2AB SAB plus minus 2B SAB alpha A minus, plus alpha B squared. Uh-oh.
How can two have an A and B?
I'm sorry, what was that?
How can the second, so it's 2AB? How is that possible? So it says alpha A plus alpha B minus 2AB. How is 2AB?
Yeah, because remember, negative B. So we're taking the negative of this guy. Oh,
Is that-
I'm sorry, 2AB.
Is that
sorry.
derivative?
There we go.
2B.
Now we're better.
Okay, I was like,
Should be-
how does the number 2 have that? Yes.
We're crazy, but not that crazy.
It's
Don't
like
limit
finding
number
pi
2.
randomly in math. He was like, oh yeah, it's there. Don't worry about it.
I would have never questioned that, like ever.
Let's see, then we're gonna run out of space. Ah!
That's what my Quizlet looked like.
Yeah. It's like when you go, has anyone ever docked a boat before?
Yeah.
Yeah, like when you
Not
you
the
gotta kill
prettiest.
the engine and you're just at drift. That's what I feel like when I write these things out. Like, I can't stop. It's too late.
Oh, I didn't give myself enough space.
Yeah.
Maybe
Okay.
short it up. I just
We're gonna make our lives a bit easier. We don't want to deal with this thing. Okay. We said way at the beginning, what type of system were we looking at? We were looking at a diatomic. Specifically, what type of diatomic?
probably helium. What is it?
Not helium. We'll say hydrogen.
Okay,
Um,
I can think better.
So we're looking at a homonuclear diatomic. Homonuclear. And alpha A is equal to alpha B, right? Because they should be the same. Alpha and beta should be the same. In our solutions, are the following. We get an energy plus, and we get an energy minus. So those are our two solutions. One's for, now if we're thinking about a hydrogen atom, what are these things?
Bonding and anti-bonding
Yeah.
orbital.
Yeah, these are the orbital energies for that system. These
Just a
are,
quick question.
Mhm.
So when you say, so we're looking at a homonuclear diatomic molecule, or are we just looking at?
yeah, we'll say molecule.
Okay.
Basically meaning H2, because we have only one set of basis functions that were 1s's. But you could theoretically think of like a hydrogen or a helium atom with a plus charge too, or so on. I could have this. Okay. Any questions so far? Cool. So we're going to use some of these ideas and we're going to tackle real systems. So things beyond the hydrogen atom. It's surprising. It's going to look complicated, but we're going to make things easier. But before we do that, let's talk about different approximate methods. So again, with all of this stuff, where does the problem become? Like, what can't we solve exactly? Like, why can't we solve these systems exactly?
Usually you're not going to deal with diatomic H atoms systems.
Well, even that, we didn't solve that exactly, right?
We have terms that are inseparable too.
Yeah. And specifically, what term is inseparable?
All of the AB terms, right?
Yep, the electron term. So we can't solve that right now. So we make approximations. To solve for a model. So you guys know some of these approximations. Tell me one of them.
Born Oppenheimer.
That is true. I meant like more
Oh,
electronic
you mean
methods.
like the orbital, the orbital approximation.
I mean more like what have we been using in lab? Tell me something in lab.
So like Hartree-Fock.
Yep.
Okay.
Give me something else.
EFT.
Yep, density functional theory. Give me another one.
Molar Plusset 2.
Yep, molar plusset. And this has to deal with something called perturbation theory. Any other ones?
There's like the UF. Oh, that would be HF.
Yep, that's HF. Yep, UHF stands for unrestricted Hartree-Fock. There's one called coupled cluster, which we talked a little bit about in lab. There's configuration interaction. And then there are what are called semi-empirical methods, and these basically take the tough parts of some of these other ones and make them easy and quick. But the problem is you have to have experimental data to build these with. There are two other ones that we're going to focus on for our last class next time. There's Huckel theory. Some people call it Huckel. All the Germans and people I knew who studied in Germany called it Huckel, so that's what I call it. And this one, all you do is you consider the pi orbitals and that there's no orbital overlap between those pi orbitals. And no orbital overlap. And then we have extended Huckel theory. And that one you consider pi and sigma orbitals. Okay. And like you guys know, the model that you pick depends on what you're trying to simulate or to model. And you want to keep these approximations in mind when you're going to model something. So if you had to pick from this list, let's say you had unlimited computational power, what would you pick?
Extended Huckel theory.
You'd pick that one? That's the easiest. Well, these two are the easier ones to solve for. We can actually do these ones by
HF.
HF's okay. It's not
Isn't
great.
like molar plusset one of the better ones?
Molar plusset's a really good one. Coupled clustered's a really good one. And configuration interaction is a really good one too.
Can you scooch the paper up a little bit for a second?
Like that?
Yeah, thank you.
Yeah, so these three are probably the ones that you'd want to choose. They're computationally expensive, really expensive. Let's say we're dealing with the real world right now and you wanted to model something. What method have you guys been using in lab to model things?
Mostly DFT.
Yeah,
Mostly DFT. Yep, DFT, a little bit of HF, right? That's what we can reasonably do right now. These guys we can actually do by hand. And that's what we're going to do next time. And the kind of crazy thing is this is still routinely used. It comes up with a simplified picture of bonding, and it can actually help you think about bonding in very easy and simple terms. So that's what we're going to talk about next time. Are there any questions about anything we've discussed today?